Okay, so let's deal with one more item right here. And this is sort of an interesting one. We've been talking about the disk method. Now, what we've really been talking about are solids with volumes that have uniform cross sections. Now, in all of the past examples that we've used, our uniform cross sections were always disks. But do they have to be? Well, the answer is no. If we have some other regular geometric shape that can form a cross section of a volume, we can form it with that. And this is sort of an interesting case like this. It's kind of hard to visualize in this case, but let's see what we can do. We want to find a volume of a solid with a base bounded by the graphs of y equals x squared minus 1, that's here in blue, and y equals x plus 1. And I've got this lying on its side, so you can kind of see I've got an x-axis and a y-axis pointed off to the side this time, right? Here's my x and y-axis, and I'm giving it a third dimension. You can imagine that we've got a y-axis going, a z-axis coming up and out of that, right? So in 3 dimensions, you've got these squares that are being formed. So on the sides, like kind of looks, some of them are larger. As you get towards the end, some of these squares are smaller. But when you put all of them together, you get this shape that's formed by these little bitty areas right here that are formed whenever this square gets larger and then eventually gets smaller. So we're going to get this shape, this weird looking, kind of odd looking 3 dimensional shape based on these two. So how do we get that volume? Well, the volume formula is actually very simple. I'm just going to go through using it here. The volume is equal to an integral from a to b, so our limits of integration. In this case, y equals x plus 1 and y equals x squared minus 1 intersect at the points x equals 2 and x equals negative 1. So that's going to be it. The whole problem is going to be our cross-sectional area. Well, what is our cross-section? Well, if you look at this square that I've drawn right here with a width of dx, my height is going to be the difference between my function x plus 1 and x squared minus 1. So what I'm really going to have right here is this square little dx width plate, I guess, if we want to think about it, with a thickness dx. But because it's a square, the length is going to be the upper function, which is our x plus 1, minus our lower function, which is x squared minus 1, which is going to become something like this. It's going to become, let's see, 1 minus negative 1, that's 2, plus x minus x squared, and that is going to be the width of each side of this square. And so what's going to happen here is our volume is going to be this formula. It's going to go from negative 1 to 2 of our square base 2 plus x minus x squared, and it's a square, right? So whatever the side is, our area is squared, right? And so if our volume of this plate is dx times s squared dx, then this is going to be squared dx. All right, so I've gone ahead and I've taken a little bit the liberty of expanding this all out. So I'm going to go from negative 1 to 2 with this function 4 plus 4x minus 3x squared minus 2x cubed plus x to the fourth dx. And you can see the difficulty right here is deciding on the sides of our shape that we're using a cross section with. But once we get it set up, it's just a little bit long, although it's not a horrible expression to deal with. So let me go ahead and get my integral for you. We're going to evaluate 4x, the integral plus 2x squared minus x cubed minus 1 half x to the fourth plus 1/5 x to fifth from negative 1 to 2. Now, making the proper substitutions in here and subtracting. It turns out that my volume ends up looking something like this, 32/5, which is what I get by evaluating this whole expression at 2, minus negative 17 tenths, which is what I get by evaluating that entire expression, 17 tenths. When I evaluate this at x equals negative 1, I end up with this volume of 81 tenths, or 8.1. So we can do that, right? The hard part right here is just the setup. So discovering that area based on that geometric formula, slicing, it's really not a big deal. Here's our volume formula that we're going to use if we're evaluating this with respect to x. Similarly, if we're evaluating with respect to y. So we can actually get these answers fairly easily once we realize what's going on. Okay, good luck with your work.